In the previous video, we obtained this unit circle, complete with coordinates for special angles. The first application of the unit circle is simply to compute the trigonometric functions for these angles. All we need to do is combine the definitions with the diagram and simply match up the coordinates with the formulas. For example, if we wanted to compute cotangent of 4 pi over 3, we first need to find the angle on the unit circle, and notice that the corresponding x-coordinate is -1/2, and the corresponding y-coordinate is negative square root of 3 over 2. Then we look at the formula and see that the cotangent is computed as x over y. So we simply plug it in and simplify to complete the calculation. Evaluating any of the 6 trigonometric functions at any of these angles will follow the same pattern. Identify the angle, determine the coordinates, and then plug it into the formula. Since the sine and cosine functions are defined by points on the circle, we can see that if we keep traveling around the circle, we're going to repeat the values. In fact, we know that every time the angle changes by 2 pi, we will be back at the exact same point on the circle. When something repeats on regular intervals like this, we say that it is periodic. The period is the size of the gap before it repeats. In this case, that period is 2 pi. Because we can either add or subtract 2 pi repeatedly, we get a whole collection of values that correspond to the exact same point on the circle. And since the point gives us the values of the sine and cosine functions, we would say that the sine and cosine functions are periodic with period 2 pi. Formally, we can express this relationship in the following manner. The 2 pi n combination corresponds to the increase or decrease in the angle after winding around an extra n times. And since the sine and cosine functions determine the rest of the functions, we see that they all have this property. We will see these again later on in this course, and for some of these we can actually find a shorter period, but we're not going to worry about that for now. When evaluating the trigonometric functions, this relationship allows us to change the angle by multiples of 2 pi without changing the value of the function itself. This lets us adjust the angle so that it's back between 0 and 2 pi, so that we can use the angles on the unit circle diagram that we had earlier. For example, to compute cosecant of -7 pi over 2, we can just keep adding multiples of 2 pi until we get to a familiar value. A third application of the unit circle is to understand symmetries in the trigonometric functions. If we draw the angles plus or minus theta on the unit circle, we can see that the x-coordinates of both points perfectly line up. This is because the upper half and the lower half of the circle are just mirror images of each other. This means that if the coordinate of the upper point is xy, then the coordinate for the lower point is x negative y. We can plug this into the definitions to discover the following relationships. Notice that the cosine and secant functions are the only ones that stay the same when we use the negative angle. There are 2 vocabulary terms that are useful here. We say that a function f is odd if it satisfies the property f of negative x equals negative f of x. And we say that a function f is even if it satisfies the property f of negative x equals f of x. In other words, the sine, cosecant, tangent, and cotangent functions are odd, and the cosine and secant functions are even. But it's important not to get hung up in the formal mathematical definitions. The key idea is to think about the geometry of the unit circle. If you take the point on the unit circle that you get with the angle theta, then the point on the circle corresponding to negative theta is the reflection of the original point across the x-axis. This keeps the x value the same, but changes the sign on the y value. This picture is more important than memorizing that the cosine function is even and the sine function is odd.